complicated would it be to build a servo decoder using the modular approach I introduced in video number 16? In the first part of video number 17, it took about half an hour to come up with a decoder that was working but did not meet most of the specified requirements. So now is the time to change that. Hello YouTubers and welcome to the Internet of Toy Trains. I am Hans Tanner and here is a new episode of IoTT with fresh ideas about how to use the Internet of Things along with sensors and microcontrollers to control a model railroad layout. So, get on board! The train is leaving the station. Here is the table of contents of this video so that you can skip ahead to the topics you are most interested in. In part 1, we built the hardware using an Arduino Nano and developed a first version of the software that can decode DCC track signals and control all 16 servos using switch commands. For details, please watch video number 17. Okay, compilation is successful. Now it's uploading. I'm going to switch to the monitor so that we see when it's initializing. Okay, so I should now be able to command servo 21. Let's test that and see what happens. Great. Then 22 is missing, but 23 we should have. Yes, that's the second one here. The next is 25. Yes. And so on. So we have a successfully working servo decoder with 16 channels, and that was just what, 10 minutes? So it's not too complicated. So now that's already pretty cool, but of course that's not what we really want, because all servos now are in a linear address range from 21, and maybe we want to just mix the servos. Also the signal commands are not handled at all, and there we have a problem because they are using some similar addresses or have the same address range, so we need to make sure we can distinguish between servos and signals. Also all the servos have the same minimum and maximum position, but not all servos are the same and not all switches or signals are the same, so maybe some servos we want to have a different range. So that's the first improvement now that I'm going to do. I want to be able to give individual addresses for each port, and I want to be able to specify the minimum and the maximum position individually for each port. So let's see how we are doing that. Let's go back to our IDE, and what we need to do now is defining a data type for our servo, and that's a structure. So I do a type def struct, and I call it my servo, and what I put in here is a 16-bit unsigned integer for the address, so that would be servo address. And then I would put in an 8-bit unsigned integer for minimum position, and same thing for the maximum position, so that I can actually specify that for each servo individually. And then the next thing I do, I define an array of 16 servos. So I do my servo and I call it like servo array, and it's going to be 16 elements long, and I can actually initialize it right here. So that means I can do the whole setup in just a few lines at the beginning of the program. So if I want to change something, I just come back here, I can recompile it, and there we go. So to define an array, that's basically how it looks like. And now for every line we are going to put in we just define first the address. So let's say my first address of the first port would be, let's say, 24, and then I can actually go with like servo min, servo max, and that would be, need some brackets here, that would be my first entry for the first port. Now I can copy and paste that 16 or 15 times. That I think should be it, and we can now assign different addresses. So let's say my second port, which really is not occupied here, is like 25, but then I go like, my next switch would be on address 50, I do it like 51, and then I go low, as the next one is 10, the next one is 11, and then it's like 16, 17, 18, and then let's say 23. So just so that we have some examples, like 33, 34, let's assume those are now consecutive, 36, 37, and then let's do like a higher number, let's say 211 and 212. I just group them like in groups of 4, so that is a little bit easier for me to find it, and I see I have one too much, which would be a problem when initializing, so I just randomly pick one out. So now I have like 16 ports defined in an array with the address and then the minimum position, the maximum position, which can be individualized, but right now I just keep them the way it is. So now we need to change our strategy when we receive a command, because that was really done actually for a fixed address. So what we do now, when we receive an address, we just cycle through that array and see if the address actually fits the address of that particular port, and if so, then we change the position of the servo. So what we do is a for loop, for, and that would be integer e equals 0, e I smaller than num servos, and we need to increment I every time we run through. And now we say if the address which comes here equals, so that makes that part easier, equals, let's see, what was the name we gave it? We gave it, the whole range is servo array, equals servo array, and now the loop variable was I, servo array I, so it cycles through, and every time it picks that particular line in that servo array. So if the address is equal servo array I dot servo error, that's how we call it. So if it's actually matching this address, then we go and say if the direction equals 0, then we do a pmw set pwn, and now it is just I, because we are already on that port, and if direction is not 0 but something else, we would actually then set the same address I of port I to servo max, and this actually should not be servo min or servo max, but it should now be servo array I, so that particular setting dot min pos we called it, and the other one should be max pos. Okay, so looks like we have one bracket too much here. So we cycle through, and if that address is equal, then we actually set it. So let's try it. Let's compile and upload to the Nano and see what happens. Again, we should have like 2450 should work. Oh, here we have an error somewhere. Oh yeah, look, there was like something's wrong here. It should be Servo Max and not Servo P Max. So let's delete that. Somehow I managed to put a character in here. Of course it does not like that. Okay. That should do the trick. Let's try again. Another error here. Oh, here, look. There's a comma missing. Let's try again. Okay. And here is a bracket missing. Or actually we can eliminate one on this side. Okay. Okay, now it's compiling. It's uploading. We can go back to our monitor. Initialization is done. Now we should be able to get something on 24. So let's try that. Something is doing something, but not exactly what we want. So let's try another 150. Okay, so what turns out is this the variable that we use as limitation here needs to be a 16-bit in order for the library to understand it properly. So now I changed that to 16 bits and everything is okay. So let's try again our 24. And let's open the monitor again so that we can see what is decoded. So 24, and it's our first servo here. Then I go to 50, which would be our second. And yes, the servo is working. I go to the high-end address to 12, which would be my last one here. And indeed, it's moving as well. So success. So now we can command control any switch number, but what's still missing is the signal addresses which come in from signal commands. But essentially we now can just copy and paste that whole thing. The only problem we are running into is that the address can be the same as for the switches, and we need to distinguish. And the second problem is that we do not have a direction, but this time it is a state. And state is basically the aspect the signal needs to display. And that can be a value between 0 and 31, which does not exactly fit with our servo min and servo max. So we need to scale it. The way I'm controlling the aspects of my signals is stop is 0. Slow approach is like a 2, then I go 4, and clear is like 8. So what I want to do is from 0 to 8 I want to scale over the whole range, moving range of the servo. So if I send like an aspect of 0, it should go to servo min or to this particular servo min position, and if I send an 8 or even more, it should go to servo max, but not higher than that, because it should not run into the hard stop of the servo. So, and for the address problem, what I'm going to do is I define a higher level address range for signal servos 10,000 and higher. So let's make an example here. I have like here I have some signal addresses 800, 802, 846 on my test layout. So I do the first one, which really does not exist here as a servo, but anyway, so I give it like 10,000, 10,800. That would be my first one. The next is 10,802. The next one, non-existent, is 10,804. And then we have a servo connected to the last port. I make this 10,806. So this way I can distinguish between servo addresses for signals and servo addresses for switches. And what I do here is, in my routine here, I say address equals 10,000. So I add 10,000 to the address. So if it comes in like as 802 from the system, I make it 10,802, which means I then can easily find it in my array of addresses that we just have. And then it's basically the same. I go through that whole array with that for loop, and if the address matches what I have there, now it's not direction, but it's state, and I need to actually put in a function that converts my state information into a position information for the servo. And what it is, I can move the servo between servo min and servo or min pos and max pos in steps of a value of 8. So I need to define the slope, and then I need to multiply it with the status information, and make sure I'm not crossing the boundaries. So that's easy enough. So the function, what I do is, my zero position would be servo min pos. I just develop the function and then I copy it in. That would be my zero position plus, and then I do like first I do the slope, which is really servo max pos minus servo min pos divided by my my highest value that I'm planning to use, which would be 8. So for an aspect value of 8, I want to be at the maximum, and I need now to multiply that with my state value. So that would be state times that difference between min and max divided by 8. So if I have a state of 8, that would actually be this difference. So if I add the difference to min pos, I would end up at max pos, which would bring the servo to the upper end. And now I have one problem, because the aspect value can go beyond 8. So what if I send a 20? That would be a value that the servo cannot handle. So for that I'm using the minimum function, and use it with the calculated value, and the other parameter I give to the minimum function is really my maximum address. So my max pos address here, I copy that in here. So let's see what happens is it takes the smaller, it adds the smaller of max pos, and actually that was at the wrong location here. It needs to go here. It takes the minimum of, so the smaller of max. So if I calculate a value that is higher than max, it takes max. If I calculate a value that is lower than max, it takes that value. and that value that I calculate is the minimum position plus my value multiplied by the slope of that curve. Now let's check, that seems to be okay. So what we do is now we copy that whole formula here into the value. Okay, so that should do the trick. Now I would expect if I send a stop, it would go all the way to the minimum. If I send a clear, it would go to the maximum. And if I send an approach or slow approach, it would be somewhere in the middle. And the whole thing would be for addresses as defined here. So 800, 802, 4, and 6 with an offset of 10,000. So let's try it. And that would be the last two servos that work this way. Okay, it compiles. That's already a good sign. Let's show the monitor again. Okay, so now we should be able to control 802 and 806. First signal 802. Let's put it to clear. Now to approach, to slow, to stop. Now let's go 806 to clear, to slow, to approach, to stop. So now we can control turnouts and signals. We can have individual addresses that can be completely mixed, not a problem as well. And we can specify individual minimum and maximum positions for each individual servo. So that's already a good step. Now there is one more thing that I really don't like, and that is that once a command is issued to a servo, it moves with a constant speed, and I cannot influence the speed the servo is moving with. So if you have some like slow motion switches, that's not really what you want. You want to be able to control the speed of the servo. Now to do that, that's a little bit complicated, because now we need to really do a two-step approach. We first, when the command comes in from this digital system, we basically just need to set a target position for that servo, and then we need to have a time-driven routine that slowly brings the servo step by step to that target position, and we need to be able to define the pace. So we need to give it like a pause between two steps if we want to. So to do that, let's go back to our IDE, and what we need to do really is to add some more variables to our definition. The first thing we need is a target position and a current position, so that we know what the actual position of the service is and where we actually want to go. So we make it a target position and a current position. And then we need kind of like a delay time, and we don't want to make that really big, so I just go with like an 8-bit integer. Oops. A move delay, and we need a 32-bit unsigned integer where we record the time of the last movement. And that needs to be a 32-bit value, because we measure that in milliseconds, and that is like a large number. So that's why we need like four bytes. So I think that's it. Of course, now we need to change the way how we initialize that. We need to add our positions. and what we do is we give an target position of, let's say, servo min, and we do a current position of servo min +1, and you will see later why that is. We do a move delay of whatever we want. If we want to go it with like full speed, we give it a 0, and for the last move we give it a 0 too. And we have to copy that into all the initializations. Okay, and now what we need to do is, when we set the value, the new value of the array, we are not directly going to send that out to the PWM module, but essentially we are just setting the target position. So we say target pos equals that value that we were looking into, and same here, only this time that would be the max pos. Okay, so now when a command comes in, we are no longer setting the server directly, but we are basically just telling the system where we want to have it. And what we are doing now is we define a new function, and we call it like process locations, that we call from our main loop, and we are just going to put in some stuff later on. For the moment we just add this command to the main loop so that we don't forget that processing. So every time we run through that loop, and that's a few thousand times every second, we call that process location thing. And what process locations does is it essentially goes through all our ports, so we really can use that for loop again. And now we check if the current position, and we can do some copy and paste here as well. So if my target position is not the same as my current position, we have to do something, right? We have to move that servo somehow. And now, if it's not the same, we need to figure out if it's like more or less. So the next command would be if, and we again can pretty much copy that. Here we need a bracket. Okay, so now if my target position is more than my current position, I would now increase my current position by 1, so that it comes closer to the target position, and I would now send this as my new position to the servo. That would be, and that needs to be actually that whole thing. So I increase the current position by 1 and send that new value to the servo. And of course, if it is the other way around, and we know it's not the same, so it cannot be, the difference cannot be 0, it's not bigger, so that means it's automatically smaller. So we basically just can copy this and change it. So in this case we do a minus minus, and that's it. I guess so. So let's try it. No, before we do that, there's one more thing we wanna add a delay here. So what we do is we make notes when we send last position command, and then we wait for the time that we can specify up here in this parameter here that we set to 0 everywhere. Let's actually make an example. Let's use the first one and put it to like 10 milliseconds delay from step to step, so that we can actually see the difference. So now what we do is we check if the current time is actually more than our last move plus the move delay. And again we do that for every port. So if servo array I dot last move, that's the time of the last movement, plus servo position I, how did we call it? Move delay, I think. Move delay, yes. Move delay. If this is more, actually less than our current time, which is in the milliseconds of the system time, so they pass along, and at one point in time they become bigger than the last move time plus our delay. So if it's more than that, oops, and we need to put that in brackets as well, then and only then we do that whole thing here. So that goes like one in, and then what we need to do is we need to set that last move time. When we are done, we need to set that to millis, so that we know when we did the last move. Okay, something is wrong here. That actually looks good. Needs one more bracket here, and we should be good. Okay, just some cosmetics here. Okay, so now we should see, for the movement of the first servo, we should see a movement step by step delayed by 10 milliseconds every time, because 10 milliseconds we actually have specified up here as our move delay time. So let's compile and see what happens. There is an error here. Oh yeah, there is like a bracket missing. It's always my little war with brackets here. Okay, let's try that again. Okay, it compiles. It uploads, it's done, it's initializing. So now let's see. Our first one would be 24. So let's select switch 24. And nothing happens. Is it? Yes, it is decoding. Aha. Okay, this here needs to go here, because of course we only need to set the time once we have processed it. So that was an error. Let's try again. Okay, now it's moving slowly and it's changing direction while it's on the move. So it now moves step by step with like 10 milliseconds time delay. And of course now I also have concurrent movement. If I at the same time move the other one back and forth, that would work as well. Great. So now I can control not only the end positions of the servo, but I can also control the speed the servo is moving to, and I have complete flexibility what addresses I'm going to use on what port, and whether it's a signal address or a switch address. So that's basically what I wanted. Now I can use that decoder on my layout. After those 2 rounds of improvements, we now have a decoder that is more flexible and adaptable than most commercial products you can buy. And with material costs of below $20, it is also pretty competitive. And if you want, you can build on this example. The first thing you could do is putting all the components onto a perf board to make it more permanent, and you could put it in a housing to make it easier for installation. Furthermore, you could add more PWM drivers to drive more servos from the same decoder. The maximum number of modules the Nano can handle is 64, resulting in 1024 turnout addresses. If you use tortoise type switch machines or solenoid type switches, you could replace the PWM driver by an I2C relay board, make some minor changes to the software, and drive your turnouts through the relay board. There are several I2C relay boards available. I have added some links to the description. Another possibility would be adding an analog mux and push buttons for the local activations of the turnouts. I am sure you have some more good ideas, and once you start playing with it, the possibilities are almost endless, and the performance of even a small controller like the Nano is enough to do ways more than what I do in this decoder. Let's summarize and draw some conclusions. Today, it is possible to buy standard components for solving the most common electronic problems. To build this decoder, we used the DCC interface, a buck converter, and a 16-channel PWM driver as peripheral building blocks to the Arduino microcontroller. All we needed to do is connecting them with a few wires, and the decoder hardware was functional. On the software side, there are also hundreds of open source libraries available. The rule is, if you can find a component for your problem, then you will also find a library that supports it. No surprise, therefore, we were able to just install a DCC library for signal decoding and a PWM driver to control the servos. With that problem taken away, we were then able to focus on the application software, which turned out to be not more than about 100 lines of Arduino code. So, as long as there are no demanding space constraints, like for example in the case of a locomotive decoder, there is no reason why we can't build these devices ourselves. The possibilities are endless. As always, I hope this video was useful or at least interesting for you. If so, please click the like button below and subscribe to the channel. I appreciate your support as well as any feedback in the comment section below. Also, check out the additional information provided in the description section. If you don't want to miss any future IoTT videos, click the bell icon and you will get the notification when a new video comes out. Thanks for watching and see you next time.